Hello, everyone. I'm Elizabeth Angel. I'm EERI's Communications and Program Manager. Welcome to today's webinar, which is the first of a series of briefings we're doing with the 3 Learning from Earthquakes reconnaissance teams that went to the field in March to study the impacts of the Kahramanmaraş Earthquake Sequence affecting Turkey and Syria. Sorry. One slide too many. Before we get started, I just wanted to take a moment to talk about EERI. If you're not familiar with us, EERI is the leading nonprofit membership organization that works to connect professionals from a wide range of disciplines in the US and around the world who are working to understand earthquake risk and increase resilience. And you can find out how to join us at that link here on the screen. Learning from Earthquakes is our flagship program, and it leads our post-earthquake reconnaissance. It was formalized in 1973, so it's celebrating its 50th anniversary this year. And both academics and practitioners from a wide range of disciplines come together to collaborate with local partners and study the impacts of major earthquakes like the one we're talking about today. So you can find out more at the learningfromearthquakes.org website, and you'll hear about some of the fruits of this kind of work in this webinar. I just wanted to take a moment briefly to mention the LFE Endowment Fund. This work is possible because of the generous support of EERI members and contributions to this fund, which makes the work that we're doing sustainable. And you can donate at that link if you wish to support it. With that, I will turn it over to today's moderator, Eduardo Miranda of Stanford University. And Eduardo, you're muted. So.
Good morning, good evening for those in Turkey and other parts of the world. We welcome you to this important webinar on this tragic and devastating earthquakes. But they are also the most important recorded events of large strike slip events that provide a unique opportunity to pair ground motion observations, some of the most intense ground motions ever recorded, together with performance of structures and the natural environment. So today we will hear of the first of 3 webinars, and this one will be on the performance of Lifelines. So with that, I'll go ahead and pass it on to Ricardo Capa, who will be our first speaker. And you see the names of the experts that went to Turkey, and they will be presenting the effects of these earthquakes in Turkey. They are experts from both Turkey and the United States, and a combination of people from academia and from industry. And I will leave it with that. Ricardo, go ahead.
All right. Can you hear me?
Yes.
All right. So the presentation today will be about 100 minutes long, and we're going to try to reserve 15 to 20 minutes at the end for questions. I'm going to start by walking the audience through the agenda for today. The presentation is split into 4 sections. We're going to start with an introduction on the investigation, so the main motivation for the trip, the team composition, and an overview of the sites we visited. Section 2 is going to focus on the earthquake sequence, so particularly the ground motions and the documented effects on the emergency response and logistics after the earthquake. We're going to spend most of the presentation on the observation from our trip. And due to the limited time today, we're going to focus on a subset of the systems we review, in particular transportation, energy, and water and wastewater systems. And we're also going to touch upon university campuses and other industrial sites. And then we're going to conclude with a summary of our preliminary observations and a list of recommendations for future studies. So starting with the introduction, there were many reasons why the engineering community was interested in this earthquake. First of all, this was the largest earthquake in Turkey in the last 84 years. The fault rupture was enormous, more than 400 kilometers long, which is comparable to the 1906 San Francisco event. This is a very economically developed region. More than 40 million people got affected, and this was an indication that lifelines existed in the region. And it was also a very unique event in terms of records, many extreme ground motion and very dense network, as Menzer is going to cover in a few minutes. So there was an indication that the lifelines could have been tested to significant ground motions. And right off the bat, in fact, there were reports of damage to Lifelines, so it was immediately obvious for the community that this could have been a great opportunity to learn from experience, and in particular, the community could have benefited from an investigation dedicated to Lifelines. I had the pleasure to lead the planning and execution activities of the Lifeline team, which included 16 engineers, 8 from US and 8 locals. And you can see our names in the slide and see our beautiful faces on the right. Our team had a wide range, diverse expertise, including geotechnical engineering, structural engineers, equipment evaluation, seismic risk assessment, and power and water network performance, to name a few. And combined, we also had a wide range of post-earthquake experience, including the most notable earthquakes worldwide in the last 15 years, such as Nepal, Japan, Alaska, and New Zealand. I'm going to start the presentation by giving a shout out to the local academics and professionals for their support to our trip. There is a lot of tea drinking in the field, or I would say also coffee drinking, and the photo in the middle of the slide kind of summarizes it. This is a casual afternoon, and it's probably my 6th coffee for the day, and I'm Italian, but this was a little bit extreme for me. So there is a lot of conversation going on in the field, and you need to understand the culture, and if it wasn't for the local, I don't think we would have been so successful. So thank you again for your support. And just to emphasize the point, I put together this slide to list the name of the people and the organization that supported our trip, either by contributing their time, their professional connections, or sharing the experience of their assets. So thank you again for your support, and sorry if I miss anyone in this slide. I also want to take a few seconds to recognize the generous financial supports of all the institutions on top of EERI that supported our trip, including Simpson, Gumperz & Egger, SGH, the Electric Power Institute, EPRI, Exponent, Wyss Jenny Elsner Associate, WJE, Jacobs, TAV Construction, Promer, and the universities of Colorado Boulder, Gebze, and HPE. Thank you for your time, for your financial support, and for letting us take time off in between projects to support this important investigation. And before I pass the baton to the rest of the team, I wanted to walk you through an overview of the sites that we visited. So here on the right, you see a map with the peak ground acceleration contour map for the main shock and the 7.7 aftershock in the north from USGS website. The solid black line is the fault rupture. So you can see all these dots. Those represent the site we visited. They're mostly distributed along the fault or nearby. And you can kind of get the scale of this region. So very vast region. We were there in the middle of March, so 6 weeks after the earthquake for 7 days. And we had 2 to 3 vans driving around for 7 days. Combined, we drove more than 3,000 miles or 5,000 kilometers. And to give you just an overview of what that means is roughly the distance between San Francisco and Boston. So we essentially did a coast to coast in 7 days. We reviewed more than 160 sites, which included hydroelectric dams, coal plants, substations, transmission and distribution assets, a bunch of tunnel bridges and roads, water. I don't know if on my side, the slide has stopped, but hopefully the list is keep on moving. All right, so here you can see the whole list now. Water and wastewater treatment plants, airports, university, LPG terminals, industrial plants, and other gas and energy sites. So very wide range, very diversified portfolio, and we're still processing the data. And today, due to lack of time, we're just going to focus on a subset of those. And I hope you're going to find the rest of the presentation enjoyable. And with that, I'm going to pass the baton to Menzer.
Thank you, Ricardo, for that great introduction. And okay, I do have the control. Let's see if I can advance the slides. Perfect. So what I'm going to talk about today is to just give a brief overview of what happened in case you did not necessarily see it in the news. But I'm not going to go so much into detail. So just to get us started, there were 2 main shocks that happened within 9 hours of each other. Magnitude 7.8 that hit Turkey at 4 a.m. in the morning when everybody was unfortunately in their deep sleep. And 9 hours later, there was a 7.7 earthquake that hit pretty close to the region. And in between those, actually, there was a magnitude 6.7 that was near the first location, which is shown with the red dot here. The 7.7 is the blue one. And almost 20 days later, there was a magnitude 6.3 in Yaylada, Hatay, which was one of the mostly impacted regions. As both Ricardo and Eduardo said, there were so many aftershocks that happened over there. It was very instrumented region. There were over 11,000 aftershocks, and to this day, there were over 550 of them that were greater than magnitudes 4. So just looking at the region, Turkey is a very earthquake-prone region. It is in between all these plates, and the earthquakes that we are talking about today, magnitude 7.7 and 7.8, happened in the intersection of the Anatolian Block and the Arabian Plate. This area is not necessarily a new seismic zone. There have been previous earthquakes that are shown with the gray dots here, and then the blue dots show the magnitude 7.7 event. That was the second one. Orange one, 7.8, which was the main shock. And then the 6.7 is the aftershock that happens right after the magnitude 7.8 shown in green here. If we look at the surface rupture, the rupture was actually very shallow and we were able to see the surface. The initial earthquake magnitude 7.7 started in this segment 1 and then continued northeast and then southwest, creating significant impact. And Ricardo mentioned there were significant length of fault rupture together with the magnitude 7 and 7.8. It was going up to 425 kilometers of fault rupture that was observed in the region, which created significant displacements. This is the displacement map that USGS put together, that you can see that the star shows the epicenters. There can be up to 4 meters of displacement, and some of which we are showing in this picture, where we were able to measure that there was a direct left lateral offset of 3 meters on the roads. Or this is from Narli, where the epicenter of the first earthquake was. There was like 2 meters of increase in the high elevated ground. So continuing on that, this earthquake, because Turkey's earthquake-prone regions up, especially after 1999 earthquake, there were several recording stations that were placed. The blue ones on this map shows that the ones that were active, and the green ones show that are not active. So you can see that in the area across the fault, there were plenty of non-active stations that might get stop recording prematurely, or they were not functioning during the earthquakes. I'm going a little fast, but it is just like for the time constraints. When we look at the recorded motions in this year, we can see PGAs up to 1.2 G, and there are several recording stations that recorded that. There were some even recorded up to 2.2 G that you can just see on the map here, but some of us visited these ground motion stations, and those locations might be a little bit more observation in terms of if that recorded motion was actual. And the highest PGA values were recorded in Hatay, which also, as I mentioned, was hit by a 6.3 earthquake. If you look at the PGA contours along the area, you can see that there were significant directivity issues with like the Antakya and Hatay being one of the most impacted region, together with Islahiye and around here. And if we look at ground motion recordings, one of the unique things about the Turkey earthquakes were there were really high vertical ground motions. The motions that I'm showing is from Islahiye, which is like going all the way up to almost 1 G in east-west direction, but also similar in the vertical direction too. And this corresponds to the site class C. I'm showing it here together with the Turkish building codes. And you are seeing that the recorded motions are exceeding the code in the periods that are greater than 1 second. When we come to Antakya, we are seeing that these recorded motions are exceeding the earthquake code, which is shown with this red light. and a red line, and even in the shorter periods, and the vertical ground motions are significantly high. The PGV distribution was more uniform, but it was up to over 200 centimeters per second. PGVs were recorded in the region, and you can imagine the impact. So the overall region that was impacted covered 11 provinces in Turkey. That corresponds to over 99,000 kilometers, over 15 million population, over 35,000 buildings collapsing, and maybe over 17,000 buildings require immediate attention. I'm not going to go over this, but it was very sad event, which ended up being over 53,000 people losing their lives, which we feel extremely sorry for, and showing our condolences, and hopefully we will learn from these effects. And as a result of it, 2 million people were displaced, and World Bank estimates the cost of this is as 32.2 million in physical damages. If you do not know what that 99,000 kilometers square was reflected to, so this is a comparison of with several different countries. The affected province was greater than Hungary, Portugal, Australia, and maybe twice the size of the Netherlands. The emergency response during the earthquake was a significant issue, and Turkey actually has a robust national disaster action plan that was developed in 2014 by AFAD, which is the Disaster and Emergency Management Authority. And immediately after the earthquake, the level of impact was identified as the one that is needing international support in addition to local and national supports. In fact, there was a magnitude 7.8, 7.5 earthquake expected in the region, and a drill was conducted 3 years ago. But the one thing that we missed, that it was not expected that all the area that will be impacted significantly from these events. There were several help that came from all around the countries, and within the metropolitan municipalities of the country to the region. But there were some items that went wrong, and I'm just going to cover them quickly in the interest of time before I pass it to Brent. There were accessibility problems that actually hindered the transferring support and rescue groups to the impacted parts of the Turkey. The necessary equipment was not able to go there. And these were due to the damages in the transportation lifelines, which we were going to cover some of them. Then there was the important critical infrastructure about the water. There were no water supply for some of the areas for drinking and cleaning. And some of the other metropolitan municipalities came into action. One of the things that we learned as we were talking with the officials over there, which when we asked what was your biggest issue, it was the people. For example, for Hatay Water Sewage Department, before the earthquake, they were working with over 3,000 people. And after the earthquake, there were less than 200 that were able to come back within 10 days to restart the operations. With that, I'm going to switch it to give the control to Brent to take us through the transportation infrastructure.
Okay. So for our transportation lifelines that we visited a series of bridges and viaducts, which we'll refer to as bridges after this point. We also looked at tunnels, roadways, and airports. In total, we visited 66 different bridge sites, and those bridge sites had a total of 98 bridges. Some of the sites had multiple bridges on the site. Of the bridges that we looked at, 2 had collapsed, 8 were severely damaged, 13 had moderate levels of damage, and 75 of those bridges had little to no damage. And the locations of those bridges are shown with the black dots in the map on the right. Common issues with these bridges included incomplete load paths from the bridge deck to the supports at the end of bridge girders. And those incomplete load paths included no end diaphragms between the girders at the supports. And there was an undersized or insufficient number of shear keys between girders at the supports. We also observed longitudinal movement of some of the bridges, resulting in walking out or displacement of the thick elastomeric bearing pads at the supports. We observed a number of geotechnical issues, including abutment settlements, embankment failures, and lateral spreading at abutments. and then leaning and residual drift of bridge piers and abutments, both in the longitudinal and in the transverse directions. To give you some examples of what that looked like, we're going to quickly go through a series of 4 different bridges that we observed. The first bridge is the Bekir-Karabacak Bridge site. This bridge site includes a pair of bridges and has important river crossing in Antakya. When we visited up on March 17th, only one of the bridges of the pair of bridges was open. And it was being used quite heavily by heavy trucks to take debris from Antakya to a dump site on the eastern side of the city. And then there at the bottom of the slide, we've included some estimated PGA and PGV values at the site. Just to note, those values were provided to us by John Stewart's research group at UCLA, and those values are the ROT-D 50 values. And at some point in the future, we will also consider directionality ground motions at each site. This is an image of what that bridge looked like when we visited on March 17th. The bridge on the left was the one that was closed. You can see the abutment settlements there, as well as the bridge on the right also had similar settlements, but dirt had been piled up so that cars and trucks could drive across the bridge. Some images of what the geotechnical issues look like at that bridge. You can see some of the embankment failures on the adjacent to the bridge, as well as the abutments and displacement of the abutments. And then on the image at the right, that is one of the piers of the bridge. We attempted to measure the residual drift or displacement of that pier. The solid line there is where our plumb bob was at, and that residual displacement was in the range of 3 to 4% residual displacement. Next bridge we want to mention is the Hatay Stadium Bridge. This site also has a pair of bridges. The road serves a hospital immediately adjacent to that area. The bridge itself is immediately adjacent to the fault. And this bridge was closed when we visited on March 18th. And some workers that were doing some activity near the bridge said that the bridge would be demolished. This is an overall image of that bridge. You can see the Hatay Stadium in the background. There are 2 bridges on the site, and it crosses the main river through Antakya. These are some images of once again, some of the geotechnical issues associated with the bridge, including the settlement of the abutments and some of the structural damage at the bridge. This type of damage was very common for precast concrete girder bridges. You had this longitudinal cracking of the web of the girder that extended out into the span a fair amount. And we attribute this largely to the lack of end diaphragms. You can see the box here trying to show that we do not have the end diaphragm to complete that load path there. And you can see the large longitudinal cracks down the web of the girder. Additionally, once again, as we mentioned, the shear keys, both at the ends of the pier caps and even more towards the middle, seem to be undersized or insufficient for the demand that was placed on them. And this particular bridge had so much longitudinal movement that there was significant displacement of the rubber bearing pads or elastomeric bearing pads, so much so that actually a number of those pads were ejected from the bridge and we found them adjacent to the piers of the bridge. This is an image of the set of piers from that bridge. There's a lot going on here, so we'll try to quickly take you through it. Just some cultural things. This is just north of the city of Antakya, but Antakya is immediately adjacent to an agricultural area. And so just an interesting side note, there were herds of sheep coming through as we were trying to assess the bridge. The piers themselves, there's quite a bit of damage here. Up at the top at the pier cap, there was cracking of that cap. There were plastic hinging at the base of the piers. There's an ejected bearing pad. The shear keys are damaged both at the ends and at the middle. And then just to give you another image of what that plastic hinge looks like, we were able to get adjacent to one on land, and that's what it would look like there. The third bridge of the 4 is the Karasu Chaya Bridge. It's a single bridge, it's near fault, serves a small agricultural area. But the loss of this bridge increases the drive time from each adjacent side by about 30 to 40 minutes. It was open to traffic when we visited. And then there's once again, some intensity measures of what happened there. It's just north of the Hatay airport. A few images of what was going on there at the bridge. Both of the embankments appeared to be sloped and actually appeared to have, there appeared to be some relative movement towards the center of the bridge. There's a number of geotechnical issues once again on the left bank here, and you can see that in the lower image, how there was an embankment failure. The pier at the middle was leaning to the west. Just some closer up views of those abutments on both the left and the right. A thing to note is many of the bridges you would have some sort of utilities crossing the bridge. In this particular case, this utility pipe had buckled. And once again, the pier, significant residual drift and actually displacement of the girders such that there wasn't a whole lot left hanging on there, as well as the pier was also displaced to the south. This bridge, the Hatay Devlet Bridge, was a pair of bridges, once again, near fault. What was interesting in this, there was a newer bridge on site and an older bridge. The newer bridge performed quite well. There's a little bit of cracking in the pier cap and some damage to shear keys, but the old bridge on this site collapsed. This is what that looks like. The new bridge is in the background. The old bridge is in the foreground of the photo, and the collapsed bridge. And you had large rotations of those piers and resulting in the collapse of the bridge segments. Just a couple of images on the right of the remaining spans that were still intact at the top of the pier, and then the one that pulled off the abutment to the right. I want to talk briefly about tunnels. We had heard before we went to Turkey that tunnels had performed pretty well, with the exception of one that had to be at least partially closed. So we wanted to see that one. That particular tunnel is the Reconnaissance tunnel. It's on the D850 highway. It's a 2-bore tunnel, and there's 2 lanes of traffic per bore. And it connects Malatya, the city in the upper right on the map, with Kahramanmaraş and Gaziantep, the 2 cities on the lower left of the map. This tunnel is closed to, but not on a fault. We had heard that it was closed, or at least one bore was closed. However, when we were there on March 20th, both bores were open. We did observe that the tunnel liner and casing were both damaged. And this is a picture of what that looks like. The liner had collapsed out of the interior portions of the tunnel in some segments. And then the outer casing as well there was a large longitudinal crack in the casing. For roadways, we primarily observed these while traveling to other sites, and they generally performed quite well. The common issues we saw with roadways were primarily geotechnical, including surface fault rupture, embankment failures, and lateral spreading. But some roads were blocked due to heavy building damage. This particular one is close to the Reconnaissance tunnel. It's along the river, had a large embankment failure. They actually repaved the road across kind of the lumpy ground as a temporary measure to get the road back open to traffic, but that road will require significant further repairs in the future. Image on the left is a road next to the river in Antakya. Once again, an embankment failure has caused at least one lane of that road to be no longer usable. And the image on the right is a temporary road that was created to get around some collapsed buildings. Just a couple of other images, a retaining wall failure there on the left, spilling debris into the roadway. And then on the right are a couple of fault rupture locations indicating how much the roadway had moved at some of the fault. And then on the lower right, that is a significant highway that runs between Maraş and Antep, and was apparently repaired after the earthquake. We visited 2 airports and got reports from a 3rd airport. We visited the Maraş airport and the Antep airport and got reports from Hatay. For the Maraş airport, it was constructed in 2019. After the earthquake, it was non-operational for about 2 days, without external power for about 20 days, but operated on backup generators. There was some cracking in finishes and non-structural damage. While we were there, we did observe some slip in some of the bolted connections of the steel structure. We had reports that the suspended ceilings and TVs fell down during the earthquake, which took about 6 or 7 days to repair, and that there were major leaks from burst sprinkler piping, which unfortunately flooded the baggage area in the basement. This particular airport was used as an evacuation center and shelter for about 1,000 people for the days right after the earthquake. And just a couple of images of what that looked like when we were there. So the left is the outside view of the airport. Interior is some cracked glazing in one of the automatic doors. Image on the left is the slip in the bolted connection, and then an overall image of the interior of the airport on the right. Gaziantep Airport, we visited the new terminal, which was constructed around 2021. It's actually so new that there's still handover ongoing from the construction company to the operator of the airport. We understand that terminal was designed using the most recent Turkish earthquake code. That airport remained operational. Its baggage handling system was undamaged. We did observe some cracking in finishes and kind of small non-structural issues. There was a little bit of evidence of movement at expansion joints, but largely no issues there. Just a few images of what some of that non-structural damage looked like. Some cracking around the perimeter of infill walls. On the right, evidence of a little bit of movement at an expansion joint and around sprinkler heads. Image on the left is the baggage handling system, and on the right is a significant escalator on the exterior of the airport. We often think of earthquakes and think about structural damage, but in terms of operation after the earthquake, sometimes many of these other systems matter just as much as the structure as well. The final airport was the Hatay Airport. We did not visit this airport. We had some contacts in Turkey who relayed some information and shared some pictures with us from this airport. This particular airport, the runway buckled. The airport's immediately adjacent to the fault. The fault really runs through the corner of the airport property. That runway was quickly repaired. There was no major damage to the terminal building. However, an entrance canopy at the front of the terminal collapsed. This was attributed primarily due to a lack of a lateral structural system in one direction. But unfortunately, some settlement adjacent to the terminal impacted some of the mechanical, electrical, and plumbing infrastructure. Here's some images from that airport and the damage that was there. On the left is the buckled runway. Center image is after it was repaired, and the right image is while they were making that repair. Upper left here is the entrance canopy that collapsed, but before the earthquake, afterward is the canopy, the collapsed canopy. Some closer up images of that canopy. It rotated and fell down, and because of the lack of lateral system in one direction, you can see some of the plastic hinging of the minor axis bending of those roof members, as well as loss of anchorage at some of the vertical columns. I want to briefly touch on the universities and what we did there. We visited 3 different universities. The 3 universities that we visited was Kahramanmaraş Sütçü Imam University, or KSU, Gaziantep University, and Mustafa Kemal University in Antakya. The KSU campus, pardon me, go back one. Not able to control. Okay, there we go. So the KSU campus was operational after the earthquake. The entire university campus had been converted to emergency housing and shelter when we were visiting in March. In particular, we visited the engineering buildings, which have been constructed around 2008 to 2010. These particular buildings performed quite well, and there was very little cracking, even of finishes in those buildings. We also visited the physical plant, observed no damage at the physical plant, even to unanchored equipment. I visited a hospital and clinic associated with that university. We did observe some limited damage at that hospital, including cracking an interface of infill walls and structure, some tile damage near expansion joints, some cracked glazing and automatic doors, and failure of a small roof structure. And for the sake of time, we're not going to show those photos. Gaziantep University was founded in 1973. There's many different ages of building and construction on the campus. One of the professors there showed us some of the old buildings and referred to them as massive concrete buildings. And these particular buildings had significant lengths of shear wall. There was very little to no damage to those buildings. Some of the newer buildings on campus are more frame type buildings. 2 of the buildings we looked at was the canteen building and the library building. In the canteen, there were cracking of infill walls, some finish related distress. In the library, most of the books in the library were located on the 4th floor, and we had reports that those bookshelves toppled over during the earthquake. There was some infill cracking on that building. We did observe some minor structural cracks and some minor spalling on the entrance stair. Out of abundance of caution, they added some steel post shores to that stair. And when we visited in March, the library was not open to students. Third and final university was Mustafa Kemal University. This particular university was founded in 1992 and serves about 25,000 students. It didn't have too much damage from the first 2 earthquakes in the sequence, but the 6.3 aftershock that was close to Antakya, it caused damage to the university. And after that earthquake, the campus was closed. We did view a couple of buildings on campus. One of those was the Agricultural Sciences building. In this particular building, there was extensive damage to infill walls and to roof parapets. We did see some electrical components that were toppled. At the substation we visited on that campus, some infill wall cracks in the substation building, but no damage to equipment. And at this point, we'll pass it off to Brad to talk about some pipelines.
Hi, everyone. Thanks for joining. I'll get us going a little bit here, talking about some of the natural gas pipelines in the region. So there's a lot of major energy pipelines that run right through the impacted area, as the figure in the bottom left attempts to try to show. The natural gas, the federal agency in Turkey that manages these things reported 18 damages to the natural gas transmission lines. Gaziantep, Hatay, Kahramanmaraş, and Adıyaman were all without natural gas for periods of time afterwards. They reported that after 5 days, the repairs were completed, but there was a lot of additional work that the distribution systems needed. Social media and news reports demonstrated that there were some rather large explosions that occurred in the immediate aftermath of the earthquakes. Google Maps shows fault ruptures crossing through alignments where some of these explosions are likely to have occurred. We weren't able to work with or contact, despite trying, government officials on these, but I think there's a lot of really important things to understand about successes and also failures of some of the various gas infrastructure and lessons we can learn from around the world, as I think many of these systems are really relevant to the rest of us in earthquake-prone areas, and we hope to learn more as we continue forward and more information becomes available. I'll switch now to introducing water distribution systems. There's four main provinces that were impacted. Those are Kahramanmaraş, Hatay, Gaziantep, and Adıyaman. They're shown in color on the right, with Maraş at the north, Gaziantep in the middle, and Hatay down at the bottom. We visited a number of different sites, pump stations, transmission infrastructure, water towers, wastewater treatment facilities. I'll kick off the water section a bit by talking about the first two water utilities, and then before I pass it off to Solchek and Robert. The Kaski Water and Sewerage Administration manages is the namesake of the earthquake and manages sort of the northern area. It was incorporated in 2016, serves about 1.2 million people. Relatively recently, a number of these province-level water utilities were developed to bring all these different towns, as you can see, under one sort of common management group, and that has helped in some ways in us being able to get some information from some of these areas, but it's also provided some different types of challenges where the systems within one of these groups can be very, very different from town to town or city to city based on how they've developed over time. And so there's a lot of variety in the characteristics of each of the systems. This is an example of the type of information that we try to pull. This is from Katski. showing specifically the city of Kahramanmaraş and some of the various infrastructure components. In this map is showing one water treatment plant, water supplied from a dam to the west at the east, spring at the west, and several wells at the bottom. Going north, the two large water sources are relatively recent, which we saw as sort of a trend in construction of infrastructure systems over the last 20 years in Turkey to support increasing populations and also to help fuel economic growth. A lot of the systems that were built recently performed generally well, and I think are really good surrogates for other places around the world. There's also 34 water tanks and storage structures and 9 pump stations within this map, which I don't expect anyone to be able to see explicitly, but just to give an idea of the number of individual sites that each of these utilities in one city makes up, and why it's really important that we build these relationships, as Ricardo talked about, with tea drinking and building collaborations and relationships with folks, which we're continuing to do with our Turkish colleagues and the utilities themselves. A couple of additional details about the Kaski water system: about 3,200 kilometers of water distribution pipeline, 1,500 in wastewater, a number of different pipeline types that are relatively similar to what we'd have in cities in the US and around the world. And the new installations are also similar in the types of materials that we would expect used in a lot of other places. The statistic here that is really mind-blowing in my mind is that this particular utility did 5,000 repairs on water infrastructure over the 40 days after the event, which is about 120 repairs per day, which is a pretty enormous number and a tremendous amount of effort from the staff and things to try to bring these systems back online and get them reinstated. The water services were reinstated, and I put that in quotes, after 3 days, except in areas where there's really heavy building collapses. That was a problem not only for the roads, but also for the pipelines, that many buildings fell into roadways and made them inaccessible. Despite getting the water back online, there were resident concerns on drinking water treatment. And so an example of what that might look like and how we think about that would be in the top right-hand corner. This is the picture from the water treatment plant, Kaski, and one of the components of the water treatment plant were these PVC pipes that had fractured in a number of different ways that were used to agitate some of the systems and some of the settling pools. And so while the treatment plant was operational and was continuing to provide water to the area, not every component of it was working, and that has effects on water quality. And so having resilient systems in each of the aspects is important, and they're working through trying to replace all of that. We also visited a number of sites where ongoing repairs were occurring. A number of weeks afterwards. The top picture there is a asbestos concrete pipe, which had been leaking. Difficult to know, but for some time, the morning we were there, a sinkhole opened up in the middle of a major throughway, and an emergency repair was necessary. Whether or not that was damaged during the earthquake or not, I would suggest it probably was, but these things are being found over time. And so the recovery process is quite long as the various areas are identifying some of the levels of damage. The Hatay Water and Sewage Administration manages the areas to the south with about 1.6 million people. 6 of the 15 districts within this province were heavily impacted, including Antakya, which the picture at the bottom there shows an example of the situation that we encountered when we were there. Most of this region was still under a boil water notice as of the 19th of March, as they're continuing to try to bring the systems back up online. They prioritized, as in other areas, repairs to transmission lines, which would be the large pipelines that are bringing the majority of water into regions. There's a number of repairs that were done relatively rapidly following the event to get primary supply to a number of areas, and there's additional information on some of those there. The town of Iskenderun is a little bit further from the fault rupture, but experienced some pretty significant liquefaction effects. The top left is a picture of a wastewater pump station that actually expels water into the Mediterranean after it's been treated. I can see significant levels of liquefaction around the supported building. A number of the various pipelines and conduits that were running in and out of the building had fallen off supports and things like that. And so the station was inoperable. Whether it was inoperable due to acute damages in this area, or if it's more related to some of the wastewater treatment plant damages, which Robert's going to talk about in a little bit. That was unknown to us at the time, but some important observations and continuing to identify what sort of the pieces of the infrastructure systems that are leading to their inability to get things back up and running. Another example is in the bottom picture here. The city of Iskenderun is supplying 2 to 3 times the normal volume of water due to damages. They have some difficulty getting water up to about the 4th floor. It's expected that there's many other repairs that are needed. And this is an indication here where we have water that is treated water coming through retaining walls into depressed roadway systems as an indication of the continual loss of supply as things go. And that doesn't really speak to the wastewater system, which we expect probably was severely damaged as well. There were successes in Hatay, and one of them was the utility's ability to provide temporary services to displaced residents. The picture on the right here shows a temporary station that is actually tapped directly into the distribution, both wastewater and water distribution system. And the bottom right is sort of a temporary water setup that goes into the mains in the ground, and then a wastewater toilet that's tapped into the ground as well. And so over something on the order of 400 of these were set up across the region to provide the most basic but absolutely necessary services to some of the tent cities and other areas. The significant challenge that was reported to us by all of the utilities was staffing, really. For example, Hatsu had about 2,500 staff. The days after the earthquake, they couldn't find 200 people to come. 34 of their staff had perished. Many people were looking for lost loved ones and keeping an eye on their property. And so those are some of the really big personnel challenges that were impacted the recovery and the ability of folks to move forward after this. With that, I'm going to turn it over to Solchak to talk about Gatski water. Solchak, you're muted.
Thank you, Brett. Actually, now I will continue with Gaziantep Water and Sewerage Administration Gatski service area. Gatski provides service to all Gaziantep province with about the number of people 2.2 million. But I want to express that actually Gaziantep takes a lot of refugees from Syria also. It is reported that is 500,000 to 1 million. So actually they are serving more people than officially stated here. Well, water to Gaziantep comes from 4 sources. You see on the picture here. One is Yüzba. Actually, the water is taken from Göksu stream here. And then there is Pazarcık. It is actually around Kartalkaya Dam. And then there are Nizmilli wells. So actually, I will explain them in a few moments. Here, water is obtained from the wells. I will show the damages actually on those the transmission pipelines in a moment, but I want to give a brief explanation here. This transmission line actually is about 85 kilometers away from Gaziantep, and 3.5 kilometers of it actually crossing the mountain here. And then the rest goes as a buried pipeline. And the pipeline is about 3.6 meter diameter here. And then here from the Pazarcık area, actually we have pre-stressed concrete pipes which are damaged. I will show the pictures as well. But only very small percentage, 2 to 5% of the water comes from the water wells distributed around the city. So most of the water comes actually out of the boundaries of Gaziantep from Kahramanmaraş area. The Pazarcık water source is about 45 kilometers away from Antep, and the water brought to the city via 1.4 meter pre-stressed concrete pipe. And those pipelines were damaged more than 10 locations. And you see the pipe brought out from the ground actually here by the excavators. And then you see those pipes were replaced by steel pipes. And then there is also a nearby 1.8 meter diameter steel pipeline. Those pipeline had only one reported damage, and actually this system was on in very, very short time after the earthquake. This Düzba water source construction started in 2016. And there is a construction of about 21 kilometers of power distribution lines, and there were damages on those system. And then there were some water quality issues. Actually, you see here right now, maybe, greenish or bluish water, but right after the earthquake, 1 week after the earthquake, we were here, it was entirely red, actually. Because of the water coming from the Göksu, and this water was not treatable. So they were not able to provide water from this source to Gaziantep. And knowing that actually 70 to 80% of the water comes from this source, it was very important. But the thing is, right after the earthquake, some people migrated to the city, and there were also damages in the distribution lines. So the need for the water was limited at that time. So the Gaziantep Gaski were able to provide to the part of the city water from the other sources. And in this transmission pipeline, there were air wall damages at 10 locations, wall structural damages, and tunnel fault rupture and fault ruptures, which I'm going to show in a moment. You see here, the pipeline is actually, getting into the mountain, and it goes about 3.5 kilometers here. And the diameter of the tunnel is about 5.6 meter here, and the pipeline itself is 2.6 meters. And you can see some of the damages here in the lining. We walked through actually all the tunnel, 3.5 kilometers from one end to other end. And there were many lining damages, as you see here, throughout the tunnel. They focused, some of the damage was relatively heavier compared to other locations. And at those locations also we noticed significant displacement observed in the tunnel. And as a result of those movements, you can see actually there were some residual offsets at the pipeline supports here. There were some fixed support damages. And the pipeline actually was constructed quite well in many aspects. They have expansion joints, which has a capacity of 7 centimeters here. And it was able to tolerate the movement itself, and we haven't noticed a separation at any location. And then eventually they started a repair shop here, and they inserted a 30 centimeter pipe here, and they were able to push both sides actually to their original location. And there was an unfortunate location, let me say here. You can see here, actually, this is a gas pipeline about 1 meter diameter. And this water pipeline, Gazki-Düzba transmission pipeline is crossing here. Because of the requirements by the gas company, they were asked to cross that area almost perpendicular to the gas pipeline. So it is actually about 80 degrees here they crossed. But you see here, you have the outline here. So this is the pipe. And here, right along this line, we have the fault rupture, which is about 4.5 meter, which especially in that area where we have a bend in the pipeline system. And you see the extent of the damages, enormous energy is provided here. There were bends in the pipeline and wrinkles here. And you notice breadth and thin here actually in front of the pipelines. And they were just stored them actually. Maybe in the future they will use them for exhibition purposes. And the third main source is the Mizmilli water source. Here, as I mentioned previously, they were using wells to provide water, and they are 120 meters deep. And there were 4 pump stations used here to pump the water to storage facility. And then the water actually fed into the city by gravity. And there are 42 kilometers of long pipeline here, 1.2 meter diameter steel pipeline. You can see actually the structure before the damages here and the pumps itself. And this is pre-event building. And what happened actually after the earthquake, pumps were fine. There were no damages with them, and they were functioning well. But the structure itself got damaged. So after long discussions at that particular location, they decided to move away the structure. They basically cut it into the pieces, and they moved it away. And they put some shelters here to protect the pumps itself. And they were working well, actually. They were providing water to the Gaziantep area, and they had plans to construct a new structure here to get rid of those shelters. And before EERI Reconnaissance, actually, I was able to visit the area just 1 week after the earthquake. And those Gazki were dealing with many environmental problems. For example, all area were covered with snow. And when we try to reach Düzba source, for example, we need to draw over the icy roads. And you can consider those areas where the buried pipeline was crossing. And they spent a tremendous effort to repair the pipelines in short time. For example, the one you saw, the fault crossing failure pipeline, they had to deal with mud, they had to deal with water, and about 45 people were working about 2 weeks tremendously here to get the water system back on. And I think I will stop here and pass it.
Sure. Thank you, Selçuk. Getting into some more of the water system here. Let me see if this is responsive. There we go. Water towers within the distribution system caught our attention generally just driving through the region. You can see in the lower left here, this is about the worst we saw, but some really significant residual drifts. These are fairly prominent structures, so communities were concerned. Some neighboring housing, temporary housing in terms of tent cities, and folks concerned about whether these needed to be demolished. Typical forms of damage, the construction was all quite similar. These inclined reinforced concrete columns with 4 to 5 ring beams along their height. The beams were quite stout, so most of the damage was concentrated at the columns. We did see some beam column joint failures. In this instance, you see no confinement visible within the joint. Other that was quite common was this hinging just above beams, particularly as you get up into the upper elevations of the tower where the planned dimensions narrow. You see here smooth reinforcing bars and again a lap splice right within the hinge region. So fairly common form of damage there. This is potentially a newer tower in the Hatay region. Again, hinging just above the beam at some of the upper elevations. This is deformed reinforcing, mechanically deformed reinforcing. And again, damage focused at the columns, which are slightly outboard of these very stout ring beams. In the Marash region, we did have an opportunity, one of our teams, to speak to the operators of the system. In that instance, again, very similar forms of damage, very similar construction of the tower, but because of the damage, they actually rerouted the system around this tower. So subsequently, customers reporting fluctuations in pressure or even no pressure, presumably at higher peak demand times. And again, these are points of concern for adjacent communities, just given their height and their kind of fragility, as we saw. Getting into water and wastewater treatment facilities, grouping these together, a lot of similarities in the hydraulic structures, but we actually had very good access to these throughout mostly the Hatay region. Wastewater treatment plants, we visited 9. We actually had a good, as Brad hit on, interview with Hatsu, one of the operators of that facility or that network. 16 wastewater treatment plants in total for their system. Just as a kind of overview, they had 10 operational at about 40 days past the earthquake. That was during our visit. 5 were still inoperable, and we'll kind of focus in on some of the reasons why today. And 1 was actually reported as destroyed, largely due to ground subsidence. They reported almost a meter, about 90 centimeters of subsidence at that facility. 3 water treatment plants were visited. We'll discuss one of those. Generally, as a class, kind of describe their performance as damaged, but still operational. Brad touched on some of those challenges. General observations, again, a lot of similarities in construction for these structures, commonalities in damage as well. Structural failures, we really saw focused in at wastewater treatment plants, dividing walls not designed for hydrostatic pressures. Geotechnical conditions, particularly seismically induced settlements, had some considerable impacts to several of the facilities. And then one that a lot of people probably anticipate is non-structural component damage and performance that continue to impact the plants when we were there. On the whole, one of the takeaways is just, again, the challenges of these really complex linear processes where you need to keep every step in the system functional for the plant to remain operational. So getting into that a little bit, again, structural damage, we'll focus in on the things that really set the plants that were not operational post-earthquake, set them back quite a ways. These are damages that will take some time to repair, not operational when we visited 40 days after the earthquake. But these are aeration tanks we're looking at. You can see this kind of racetrack shape, oblong shape, with 1 or more dividing central walls. You also see these elevated walkways that serve as sort of de facto braces, stiffening the walls and connecting them to the exterior walls, which are containing and designed for hydrostatic pressures. The common cause was pour joints at these dividing walls. We'd see those often isolating the midsection of the dividing wall from the braced portions at the walkways. But left to perform as a cantilever, many of them just weren't up to the task, and a majority of them we saw wastewater treatment plants collapsed. You can see the missing segment here is below water with damage to the piping that used to sit atop it. Looking at a slightly different configuration, again, similar shape, similar dividing wall, this time opposing walkways at one side only at opposite ends of the wall. Damage was really pull out of these walkways from the wall progressively, and really as they became compression only elements, promoting this torsional response that really damaged the dividing wall as it collapsed. You can see it partially collapsed here on the left photo. Looking at again, geotechnical aspects were a considerable factor, especially at the wastewater treatment plants. These tended to be situated for gravity flow at kind of the low points or the middle of this large alluvial valley, often pretty close to the fault. We saw seismically induced settlements up to 25 centimeters. Generally, the tank structures and hydraulic structures did reasonably well in terms of settlement, but even you can see here two closely spaced tanks with free field settlements measured at about 16 centimeters between them. So the demands on interconnecting kind of below ground piping and other infrastructure were considerable and led to some damage. In the upper right here, you see a basement kind of pump area in the process, and it's sitting in about 30 centimeters of water that's infiltrated. The operators believe that was from a number of below ground pipe breaks that hadn't yet been investigated. And then here, I believe this is a digester structure, but you see a containment breach, whether in the piping or in the structure itself, unclear. But again, meaningful impacts of pretty large settlement there. Water treatment plants, one we'll talk about here is in Karakai, Hatay region. This was a little more subtle, a little more interesting. Settlement up, this is situated up on a hillside. So settlement considerably less, on the order of only about 5 centimeters, measured in a couple places. But this facility uses a number of weirs in some of their processes. So they had basically what we're looking at here is one of many bays of these what we think are sedimentation weirs, and they're fed by this unregulated gravity feed water channel at the middle of the building. And you can see where the red arrow is. This is an area of relatively higher settlement. And so now these what were once evenly flowing weirs, you have an area at the arrow of really rapid flow with little opportunity for sedimentation. And then the adjacent weirs, because the flow is unregulated, they're generally now stagnant ponds. So again, even localized impacts based on the layout of the facility can lead to pretty meaningful global impacts to the efficacy of that process. Non-structural damage, again, this is one we see in many earthquakes, and I think many people probably anticipated. Control panels, cabinets, equipment, we saw many things either unanchored or anchorage failed quite quickly. Often these were just righted post-earthquake and put back into position. We'll focus in on some of the larger components that really impacted post-earthquake operation. In the photo here, what you see is a larger generator displaced in the east-west direction, which is kind of the photo background, about 30 centimeters. So you see several good things going for this generator, right? It had an integral fuel tank in its base. The electrical connection was fairly flexible. The exhaust connection to the building, again, fairly flexible. You see it hung here from the ceiling, and even a flex duct between the exhaust system and the generator. So a lot of things that were able to take up substantial east-west displacement demand here as the generator slid right out of the building. Even the minor component of north-south, basically left-right in this photo, displacement, did cause the cooling structure to contact the building and led to an oil leak. So the entire generator was not operational for the many days of power outage that came subsequent to the earthquake. Another piping, again, we saw some considerable lengths, unbraced lengths of piping that led to damage. This is, again, in the Hatay region, Narlika wastewater treatment plant. We see in the lower left fractured PVC piping generally focused around joints. At the middle here, these are fairly large. These are about 30 centimeter steel pipes going up from one process to another. Very limited bracing in the way of these light gauge straps that tended to fail at their bolted connections. And the pipes actually only protrude just a little bit over the corner of this wall. And were they to rattle around a little more, they could have come free and fallen completely. On the right, this one's a little more unique. These are actually filter media or what were referred to as membranes on the site. These came loose from their attachments within the tank, subsurface, and actually floated to the top. Whatever type of membrane was used, it was reported to us that having dried out now and floated to the surface, they were irrevocably damaged. So now, in addition to the other repairs, procuring new filter media for this plant will be another challenge. Lastly, and this was probably a problem for many buildings, but infill masonry fallout was a problem in a number of places. These plants tended to have several smaller buildings housing different processes, particularly at older facilities. You see in the lower left here, this is Antakya wastewater treatment plant, a large number of buildings with hollow clay tile fallout that impacted equipment and operations. And then even at the newer facilities, this is a water treatment plant again at Karakai. You see partial collapse of this infill unreinforced masonry wall, but it's actually leaning over this gaseous chlorine tanks and piping system. So again, kind of ongoing hazards that prove difficult to remediate post-earthquake. So with that, I will kick it over to Ezra.
Thanks, Robert. I'm going to discuss the electrical transmission distribution system and the performance of substations. I'll start by providing a little bit of background on the system and overall performance, and then show a number of examples. So first thing to know is that much of Turkey has underground lines, with the exception of older areas. And the region affected by the earthquake happened to be an older area. So there were a lot of overhead lines in the transmission and distribution system that were affected. There was substantial reported disruption to electrical power service immediately after the earthquake, and this took varying amounts of time to be restored. And in some cases, I think there are still disruptions in the transmission network, but it's more intermittent now. And one example of the extent of the damage is reported by one of the distribution companies is in Antakya. They had to replace about half the distribution system, took about 2,000 workers, and they deployed 500 cars for that. But one positive is that there were no reports of conductors starting fires. So overall performance, transmission and distribution overhead structures generally performed well, but there were some exceptions. And these were when there were geotechnical conditions that led to damage, if there were adjacent failures that impacted overhead structures, or in many cases, there were insufficient pole anchorage into the ground. Outdoor substations would experience equipment damage, but this was relatively minor. Substation buildings, on the other hand, experienced both equipment damage and the collapse of the buildings, and these were substantially impacted by adjacent structural failures. So we'll look at some examples now. So one is, we can see on the left, a collapsed transmission tower. I think this is a 220 kV line. So this collapsed because there was a landslide that picked up two of the legs of the tower and moved it down the hill with the landslide, while the two remaining legs were left up in the hill. So you can notice on the right-hand side that the next tower in the line is perfectly fine. No landslide in that location. It was subjected only to inertial forces. In terms of the magnitude of that landslide, you can see that the spacing between the legs of the two that didn't move in the landslide was about 34 feet. And after the landslide, one of them was now 48 feet away. So this was a substantial landslide that collapsed the tower. This was not the only instance of geotechnical impacts. We also saw some instances of rock falls. In this case, the rock started all the way at the top of that hill and rolled all the way down and took out a number of distribution concrete poles that were then replaced by wood poles. Now, this rock slide also blocked the road, so they weren't able to bring in cars to access it. They actually had to come in by helicopter to replace the poles. So you can see what one of those concrete poles looks like on the left-hand side when it's hit by these rocks coming from above. And this wasn't just a local impact on one or two poles. This was all along this road there were impacts. So on the right-hand side, we can see pole after pole, this wood replacement poles that are in place. As I mentioned, there were a number of pole anchorage problems. So this is in Antakya. If we look at the way these poles are anchored, there are these small concrete footings that hold them up that don't appear to be reinforced at all, or at least not heavily reinforced. And so they're subject to cracking or just breaking and the whole pole rotating out. Here's some more examples of rotating poles on the right-hand side. We see the after version of what's shown on the left-hand side, where I think this one got tugged by the conductor as well, and the pole fell off, and you can see what one of those pole foundations looked like in the photo on the far right. And it just fell off cliff here, right next to a bridge. And if we look out in the field, sort of away from the more densely populated areas, the number of poles and lines that are leaning from these similar types of pole anchorage problems. In urban areas in particular, there were numerous issues where structures would collapse or would have debris fall off them right into the distribution system. So here's an example in Antakya of a lattice pole that was hit by a collapsing structure. Here's another example where one of the precast concrete poles that was along the street was hit by a structure that collapsed into the street. And one more example for good measure of a concrete pole that was hit by several collapsing structures potentially took this one out. And in addition to the debris just hitting the structures, it could also land on the conductors, and then the conductors would pool on the top of the poles and would deform the pole. So this pole is leaning maybe 10 or 15 degrees because debris hit the conductors. In some cases, there were failures of concrete poles, which may purely be attributed to inertial force issues. This typically was when there was some sort of deficiency. So in this case, there were relatively smooth bars and very small stirrups that were lightly corroded, but because the stirrups are so small, that stirrup wouldn't spall enough concrete that you could actually notice that there was a problem there, and the stirrups fractured quite easily during the earthquake. Here's some more examples of poles that failed from inertial forces, and in one case, I think the conductor displacing and ripping off that cross arm. There were equipment damages as well. On the left-hand side is a piece of equipment mounted on top of a pole in Elbistan that fell off, and then on the right-hand side, it looks like a mobile piece of equipment that fell over. And I'm actually not convinced that this was here before the earthquake. It looks more like the mobile equipment that was put in place after the earthquake to provide power that has perhaps fallen over because someone pushed it or because there was an aftershock in the area. Now, moving into substation buildings, there was a full range of types of damage to substation buildings. Now, these are in a lot of the Hatay region. They have had substations above ground, and they've moved, in some cases, put them underground, but these are largely above ground. So the left-hand side is an example of one that looks relatively undamaged, although some structures around it were damaged. And then in the middle, we see one where some of the infill has fallen out. And on the right-hand side, there's one that has collapsed during the shaking. And so these have a variety of different amounts of equipment in them with varying performance depending upon whether they were hit by infill or not. So here's an interesting example where the actual substation building was fairly heavily damaged, but the equipment inside was completely fine. Then on the right-hand side, by contrast, in Adana, one that has been wiped out. Moving on, a common example, and these are substation buildings that are basically double height structures that don't have a floor diaphragm, where in a house, for example, you would see something. They just have some ring beams going around the outside at that level. And so those joints are particularly vulnerable to damage. So if we look on the right-hand side, we can see that some of the rebar is starting to buckle in that beam column joint area, and there's not really anything confining that rebar. This is another interesting example where we had an old substation built in the 1970s on the left side and a new substation built just a year or two ago in the middle, and then a temporary one put in place after the earthquake as well. And so in this case, the old substation was relatively undamaged. I think there was some damage to the tile at the roof level, but the new substation had substantial damage to the infill, including falling on the equipment. And so here's a photo of that new substation, the structural aspect. If we look at where the damage is occurring, it's right at stiffness discontinuity, and it's unclear how much confinement is being provided via some stirrups here. Certainly don't see any. The old substation, on the other hand, took a peek inside, and the equipment is looking pretty good. There were also substations that were affected by collapsing buildings around them. On the left-hand side, we see a substation in Antakya with a minaret from a mosque next to it. And that minaret collapsed on top of the substation, destroying a lot of the equipment in it as well during the earthquake. So they very quickly have put up replacement equipment in place that we see in the right-hand photo. Substations were also impacted by the rockfall. So this is down the road from where the concrete poles were taken out. This substation was hit by some large rocks, but fortunately, where the rocks made impact in the substation building, it was the opposite corner from where the equipment was in the building, because that equipment was actually okay. Substation equipment that was sitting out in yards had capacity for falling off of its supports or for the anchorages failing. This is one in Antakya. A lot of the equipment, though, was damaged from infill falling on top of it or the equipment falling over because it wasn't anchored at all. And of course, there were outdoor substations as well. This one was only about 1,000 feet from where there was a 10-foot fault offset in a road. I think this photo was already shown of the fault offset. In this case, there were just some toppled transformers. So overall, I think the picture is that overhead structures are not particularly vulnerable to inertial forces, something I think we've known in the community, but they can be highly vulnerable to geotechnical conditions if they're present, and they can be quite vulnerable to conditions around them, to their environment. So buildings collapsing on them or collapsing on a conductor that then pulls on the overhead structure. The equipment in overhead structures and in substations can also be vulnerable to anchorage failures. In the substation buildings themselves, if they lack proper detailing of joints and they have infill walls in intense shaking, that can spall and that can damage equipment. So with that, I'll pass it. I'm not going to pass it yet. I'm just going to briefly touch on industrial facilities, and I'll use this as a bit of a teaser for reading our full report because we only have a slide or so on this. So industrial facilities often are not considered as part of Lifelines. I normally wouldn't think of them as such, but I think a lot of them are. And one example of that are silos. So silos contained a lot of the grain, which is quite important in an agricultural region. If you can't feed your livestock, then there's a huge problem for a lot of people living in the area. There were many silos that collapsed at a number of facilities that we visited, such as this one on the left. So this, I think, was the only silo that was empty, and there were 15 others like it that were full and collapsed during the shaking. And it's not particularly well braced. And one of the issues too is that these can interact with each other because equipment tends to attach the top of one silo to the top of the next silo. On the right-hand side, we see an example of a silo, not in Turkey, that has more sufficient seismic bracing. And so then another example of an industrial facility was a corn oil plant that received, I think, a relatively light or moderate damage rating when it was visited by authorities. But there are a lot of problems at this facility, and I'll just highlight one of them. We can see that there's basically no vertical load carrying capacity of this column, and the facility is just leaning on top of the tanks and is supported by those tanks. So that's a bit of a teaser on industrial facilities. So hopefully you can read our report and learn more about them. I'll now pass it to Merve to talk about performance of hydroelectric facilities.
Thank you, Ezra. There are several hydroelectric dams in the affected regions, spanning power generating capacities from 3.1 megawatt to 510 megawatt. Within the scope of this field trip, we visit 5 electric dams that do not have black start capability and were subjected to PGAs of up to 0.46 G. As you can see in the map, 2 of these dams, which is Menzelet and Kılavuzlu, are in Kahramanmaraş. And Alabalık Dam is in the Adıyaman, and Berke Dam is in the Osmaniye, and the Karatay Dam is located Hatay, one of the most damaged provinces. The overall performance of these hydroelectric dams was very good. All the units were up and running once they received power back from the grid, which took 3 to 6 days depending on the location. Let's examine the observation for these dams in detail. First one is Alabalık Hydroelectric Dam. Alabalık Dam is the river dam with a power of 5 megawatt, and it's located very close to the fault, as you can see on the map. In this dam, slope stability issues upstream, cracking in some concrete structures, and nearby landslides have been observed. Estimated PGA values belongs location of this dam for 7.8 magnitude earthquake is 0.4 TG, and for 7.7 magnitude earthquake is 0.26 G. In these figures, you can see the landslides examples. In these figures, yellow circle represents the slope stability issues upstream, and the red circle represents concrete crack example. Menzelet Hydroelectric Dam is a clay core dam with a power of 124 megawatt. Its construction finished in 1992. This dam performed very well. Only some rockfall occurred, caused roadblock. Oil leaks into transformers have been observed in this dam, but it is not known that whether it happened before or after the earthquake. Estimated PGA value belongs location of this dam for 7.8 magnitude earthquake is 0.18 G, and for 7.7 magnitude earthquake is 0.12 G. You can see the example of rockfall in the figure on the right. Sorry. On the right, it is a huge rock, and you can see the left landslides with the yellow circle. Close to dam is a clay core dam as Manzeret with a power of 54 megawatts. Its construction finished in 2012. This dam used for irrigation and electricity. This dam also performed quite well as Manzeret dam. There is no equipment damage. There is only minor lateral spreading at crest of dam. Almost 300 local people went to dam after earthquake because they thought it was a safe area. Estimated PGA value for belongs location of this dam for 7.8 magnitude earthquake is 0.18 G, and for 7.7 magnitude earthquake is 0.11 G. Lateral spreading of dam crest is observed, as you can see in these figures. Berke Dam is a concrete arc dam with a power of 510 megawatts. Its construction finished in 1999. In this dam, EERI team observed minor vertical tilting of concrete art. Estimated PGA value belongs location of this dam for 7.8 magnitude earthquake is 0.14 G, and for 7.7 magnitude earthquake is 0.06 G. You can see the images of Berke Dam from different point of view and angles. Last one is the Karaçay hydroelectric dam. Karaçay dam is power doubled 65 megawatts. Its construction finished in 1999. This dam stores 35 million meter cube of drinking water. In this dam, there is no damage, only accessing road had rockfalls and slope failures. Estimated PGA values belongs location of this dam for 7.8 magnitude earthquake is 0.31 G, for 7.7 magnitude earthquake is 0.01 G, and for the 6.3 earthquake magnitude is 0.46 G. You can see the images of the Karaçay Dam from different point of view. Thank you. That's all for the dams. Burcu goes there.
Thank you, Myra. Okay, so I will be talking about coal and gas plants, starting with coal and gas plants and continue with other facilities. For the coal and gas plants, we in the region, there are 8 plants which are fueled either by coal or gas. We were managed to visit 3 of them as the permissions were quite hard to get for these facilities. All these 3 large coal plants were heavily affected. They have 10 units in total. Afshin plants A and B on the top here have 4 and 4 exact similar units, and Iskenderun here coal plant has 2 units. They have a combined capacity of 3,900 megawatts. They started operations between 1980s. So the facilities have been growing up until 2019. These plants do not have black start capabilities, which means that they cannot restart their operations until there is a full evaluation and inspection is carried on to get them clear for operation again. And all the online units, which were all the units which were online during the events were tripped due to the turbine vibrations, and they are heavily damaged compared to the ones that they are offline. So let me continue with the Iskenderun plant first. So the unit 1 was online and unit 2 was offline at the time of the first event. And because of this reason, Unit 1 was more affected than Unit 2. Unit 2 is up and running, starting from the mid-March. A couple of things that happened in this plant is a gas chamber moved 60 centimeters laterally and hit steel members and damaging them. There were some swinging pipes and shock absorbers and supports were damaged as well. One elevator was out of rail following the 7.7 earthquake aftershock. Transformers, they're not generally well attached to the ground or well attached to the rails that they were put on. So some of them were broken out of bush, and the other transformer moves 10 centimeters laterally, as you can see here. But they were all operable, and some glass reinforced seawater circulation pipes with joint displacements exceeding their design tolerances were observed. This caused some minor leaks on the system, but again, this was not a big deal for the operation. PC control cabinet with circuit breakers caught on fire, and they had to replace it. That was one of the major events happened here. Falling ceiling tiles, we have seen this in nearly all of the plants in the control and on top of the control board and the operators in the control room. But generally, these did not cause major damages on the system equipment. In this plant, there's 2 to 4 centimeter settlement around the turbine building, but the important structures were on 80 millimeter diameter deep soil mixing columns extending up to 45 meters vertically. So Afshin plants A and B have the same exact configuration. Both have 4 units, which has 330 megawatts capacities. They were built 20 years apart. All units were offline in mid-March, and they are not planning to start it in the next couple of months as well. There's shortage of workers since the area was affected by the earthquake, and the workers had their families and they had to move out of town. And so it's a very, very major problem with the plants. And the boiler system leaks caused a tremendous amount of problems with the restarting abilities of these plants as well. A couple of other things. We have observed 15 centimeter vertical settlement at the ground floor of the powerhouse. Here you can see on this image, but none of the electrical or mechanical components installed on or near the surface appear to be damaged. One major thing was one elevator was crushed by its own balancing concrete block. We have observed minor vertical cracks on the base columns of concrete cooling tower. And in the boiler building, there were evidence that pipe banging against adjacent steel frames. So Plant B operator reported most of the damage was observed at elevations above 40 meters from the ground. So this is in the cooling towers mostly. They have a lot of steel equipment, and they have minor and major damages on these levels. So it goes up to 80 meters. So they need expert inspectors to go over these facilities before they can be operational again. The parts related with the transmission systems is half dozen tall insulators broke their ceramic parts or their connections. One step-up transformer suffered from a couple of bushing breaks, and another large one here, as you can see, had a 15 centimeter pipe connection, and it failed, and the oil leaks from this part. But there are no fires or reported for this transformer, and it was they changed the gasket and it's operational again. Let me continue with the LPG and the industrial gas facilities and petrol stations. LPG is generally used for heating and cooking appliances and other industrial applications all over Turkey. So you can see here, we have 3 terminals here located on the coast, and we had 3 bottling and storage facilities. These observed PGAs up to 0.64 Gs. Let's continue with the PG terminals. So these are 3 terminals right next to each other. They have 20 large circular gas storage tanks and spheres built starting from 1980s. Several buckled steel braces supporting these tanks were observed. These were designed only for tension only. They observed minor leaks at flanges, which were quickly resolved. And one fluid fuel tank with floating roof spilled 6.5 tons of fuel, but did not catch fire, no ignition. It was rainy conditions, so it was lucky in their behalf. So one thing that happened here, so as you can see on the coast, it's a 10 kilometer plus lateral spread site. What happened is, it is right after the spare tanks are located right next to the main push. So it's slided 50 centimeters, and this slide caused major cracks on the boundary walls, but they did not affect the spherical tanks much. Haska's facility is another production facility. Here you can see this is the production line facility it was. So the columns extended on the side, so the roof collapsed and all the walls collapsed as well on top of the production line. So they had to remove them all from here. And so they have these tanks horizontally aligned in place still. And the only thing that they have observed here were some cracking at the supporting piers. We were able to go to Kahramanmaraş to visit some industrial gas storage and production facilities as well. One of the main sites is one that is serving to hospitals and food production facilities. They are serving oxygen and nitrogen. So there are numerous medical oxygen and nitrogen gas bottles overturned. Each one of these blue bottles have 250 ATM pressure in it. No gas releases were observed. One of the major things happened in this facility was the lateral translation of 90 centimeters. This tank, literally translated, it was 60% full, which means it is. So this has the capacity of 500 tons of liquid oxygen capacity, and it's like 300 tons of liquid oxygen. So if it were to explode, it would have been a disaster for the entire facility. But it did not. But it was not actually restrained here, so it was free to move sideways. So they have observed overturning as well, but luckily these were empty tanks. The same company had the gas production facility as well, so it's a little bit further away. So it's one of out of 4 pressurized oxygen production facilities in Turkey. This was built in 2017 to withstand high seismic loads, higher than the code requirements. The owner requested this, and this increased the overall construction costs by 30%, but this was the only site which was operable after the major earthquake out of 20 in the industrial park it was located. There were tall, flexible tank anchors, 5 center diameter. As you can see, the anchors were deformed, but they were in place. I mean, no major damage here rather than these anchors. Yard transformers came off as the vertical and horizontal restraints were missing. About petrol stations in Antakya, we were not able to investigate them in detail, but the pump stations with canopy structure adjacent one-story structure accessory building is very, very common. Vast majority appear operational and relatively undamaged, but the one-story buildings were somehow much more damaged than the canopy structure itself. LPG only reported 15% of the 330 local petrol stations were inoperable following the earthquakes due to the floating tanks and the toppled anchored equipment. I'm going to finish with the wind turbines. So we were not able to visit any of the wind turbines up close, but from our visits within the other sites, we were able to take pictures. We haven't seen any observable damage. And also we asked questions to the locals about these wind infrastructure, and they reported that they were not significantly affected. But we haven't seen any other reports, but it has to be investigated in detail as well. So I'm going to pass over to Ricardo for the closure.
All right. So in conclusion, and I want to emphasize everything we presented today is preliminary and is limited to the sites we visited. But overall, the first impression we had by traveling through this region is that the Lifelines performed relatively well if you consider the unique earthquake sequence. So for example, the hydroelectric dams were operable once they got power back from the grid. The grid itself performed very well. They were up and running within a week. The LPG terminals had no major disruptions. Most of the airport's buildings performed well. In some cases, the operation were halted by damage to runway or equipment, but nonetheless, it was resolved within a week. The university campus structures that we visited had limited damage, and some of those structures functioned as shelter areas in the days after the earthquake. And one of the 2 units in the large coal plant in the Scandium Bay was up and running 6 weeks after the earthquake. Nonetheless, I want to emphasize that some lifelines got hit harder than others. So we talked about transportation, multiple bridges near the fault rupture got heavily damaged. And you have heard of the large amount of debris that congested the traffic in large cities in the days after the earthquake. The water and wastewater system was probably the most affected of all. Several treatment plants were still inoperable in the days, when we visited in mid-March. And water and wastewater was still delivered below code requirements in terms of chemical composition 6 weeks after the earthquake. The energy system performed well, but nonetheless, there were 2 large coal plants in Elbistan that were still offline in mid-March, mainly due to a shortage of skilled workers and issues with the supply chain to get replacement parts. And Ezra talked about the many collapses affecting the substations. The few industrial facilities that we visited performed well, especially if they were on deep soil mixing columns or piles. This was consistent throughout the region. We did see some precast structure that collapsed, and this was, again, not the focus of our trip, and I'm sure we're going to get additional insights from the building team presenting in 2 weeks. Hospitals are typically considered lifelines, but there was a separate EERI team focusing on those, so we did not review those in detail, and stay tuned for the hospital team webinar next Tuesday. All right, so after this comprehensive presentation, the question is, what can we do next as a community? So we put together a couple of slides to throw out some ideas on what to do next. So some recommendation for future studies and further data collection. And I'm going to start with mentioning the lifeline system that we did not cover. So especially natural gas transmission and distribution facilities. We knew that there was reports of damage. We tried a couple of leads in the field in March, and we were not successful. So there is a gap there, and perhaps someone could take the lead in reviewing those. The wind system did not appear to be heavily damaged, but nonetheless, I haven't heard anyone taking a closer look. So perhaps someone can explore that system. We did not look at solar and telecom. It would be interesting to keep on documenting the performance of facilities that were still recovering at the time of our visit. So in particular, the power plants in Elbistan and the inoperable treatment plants document the damage and the restarting operation after coming back online. I think one of the main topic of interest coming out of this earthquake, besides the many building collapses around the region, is what I call seismic interaction. So we talked about structures falling on structures, structures falling on equipment, equipment on equipment, rockfall on structures. So there is a wide range and large number of those. And I think the community could benefit from taking a closer look at those. So throwing a couple of ideas in this slide. It would be interesting to review the equipment classes that are most vulnerable to high frequency impact loads. It would be interesting to document typical structure-to-structure interaction damage such as pounding or collapse footprint to inform future cordoning activities. So this goes back to the idea, for example, if you have an earthquake in San Francisco and a skyscraper collapses, how much of an area would you have to make unavailable to the public in the days after the earthquake? And also rockfall, so documenting the distance of the rockfall and what happened after they impacted the structures, lifeline structures and equipment. We talked to some of the locals were mentioning that progressive damage was, especially in the Ataki region, was important. For example, the university in Atay closed after the third earthquake, and I've seen power plants in the north receive most of the damage from the second earthquake. So there is a question there. What if a lifeline structure performed well after the first earthquake, but got heavily damaged after the second and the third? Does that represent a successful performance from a code standpoint? I don't know if we have the data to answer the question, but nonetheless is an interesting one for the community. It will be interesting to correlate the performance of lifeline structures and equipment with evolving standards requirement. So looking, for example, and when these structures and equipment were constructed and installed, the local ground motion and the soil stratigraphy and geology, and try to understand if these improvements we are implementing in the code are really efficient and effective. And last but not least, the buried infrastructure got hit pretty hard, and the local utilities are still discovering damage. So the complete tally of the damage is still unknown in some cities. It would be very important to keep on documenting the damage as it is discovered and document their restoring activities. And I'm gonna end this section with just last few thoughts. You've heard from Eduardo and Elizabeth. The joint EERI report is available online, so look out for section 7 on lifelines. We are also planning as a team to document our lifeline-specific observation and conclusion in a separate report later this year, so stay tuned for that. We are also planning to upload our data on public databases such as Design, Safe, and SiteEye. And I've been in touch with other research groups that are considering follow-up trips to Turkey in the next few weeks or months. And if anyone is interested in reviewing lifelines, please reach out to us. We will be more than happy to share our experience. And I'm going to conclude the presentation by giving another big shout out to my team, Lifeline team members for their support. And just for the audience to know, we were the last EERI team to deploy, and we most likely collected the largest data set of all the teams that had been to Turkey so far. And we were the first EERI team to deliver a webinar. So thank you guys for your amazing effort and for squeezing this activity in your weekly agenda. Very important for the community. So, and with that, I'm going to open the floor to questions, and we'll try to answer most of them. We have about 12 minutes left, and if not, you can see our emails on the right.
Thank you very much, Ricardo. This is a fantastic set of presentations. We reached almost 400 attendees, and we've been trying to answer lots of questions as they were coming in. And here I will read just a few of them and try to follow up. I'll start with one by Tulaniatsi, who mentioned, great presentation. Any reason why higher structure building were damaged more than bridges? Have they used different building codes because of different levels of damage to the structures?
Sure. I think we had another comment like this as well. Different building codes is one example. Certainly lifeline structures are generally designed to a higher level of performance as well, right? In recognition of their importance to the community. So I think the level of detailing, the level of engineering, the level of performance objective is considerably different between the two. The other is that many of the lifeline structures you saw here today, with the exception of perhaps some of the power plant structures and the water towers, they're generally low-rise structures, often quite stiff with large diameter columns or a number of shear walls. And that's kind of in stark contrast to the typical building stock there with rather small gravity concrete frames with limited detailing. So different levels of detailing and performance and different levels of displacement demands, I would say.
Thank you, Robert. Another question is from Kishore Hajwal from USGS, and he writes, great coverage and some wonderful slides by the team. Thanks a lot for your hard work. I'm curious if the team can shed some light on key contribution factors to pipeline damage, gas versus water, for example, shaking only versus damage to ground failure, fault displacements, landslide, liquefaction. Thanks again.
I can give a little bit of perspective. It's pretty material dependent and differs across the region. A lot of the gas pipelines were fully welded but welded steel, and so they did pretty well to shaking as we might expect. But the fault rupture scenarios seem to be more important, and we're unsure about other components that may have been affected by shaking and led to that. For the water distribution systems, it's also somewhat dependent. It seems as though there were a lot of reports of damages of understrained joints pulling out, and that could be a combination of shaking. It's possible, but most likely levels of ground movement in different directions to get that level, and then also the age and rigidity of the pipes. So some of the older cast iron and things like that, we would expect that some of the ground shaking would be a little bit more severe for some of those systems. So we're working very hard to continue to build relationships with some of the utilities, at least particularly on the water side, to try to get some more detailed information, and we hope to be able to share. And Solcek, I think I did okay, but you might have another thing to add there.
Yeah, thank you, Brett. We see actually for the transmission pipelines, the fault crossings actually and permanent ground deformations are quite critical. For the distribution pipelines, I think to make any separation between the shaking and the permanent ground deformation effects, we need to work on them. Actually, we got, as you said, quite a bit of damage reports from the water utilities, but we are required to categorize them actually. Because right now the damage numbers are lump sum numbers. It will require some work to separate them and identify them with respect to shaking and permanent ground deformations.
Thank you very much. I think what you mentioned, Brad, about directionality, it's a very important aspect. If you think about it, we have been treating seismic intensity sort of like temperature or precipitation as it's a single value, but we've known that it varies significantly with orientation. And when it comes to lifelines, it's completely different. And actually at USGS shake maps, this has been partially taken into account by looking at the maximum of 2 recorded intensities. But I wouldn't be surprised if in the future we change this practice and we really move into accounting directly for directionality. I want to move on to a third question that is asked by Theodoros Rosakis. Very, very interesting question. I will read it. Thanks for your detailed presentation and excellent explanations. My questions concern different kinds of structures, especially in the epicentral region. Was this really a mega earthquake? Should we expect some RC buildings designed according to the highest seismic risk demands and ductility potential based on modern codes to collapse during this earthquake? Should we revisit these to ensure we avoid human losses? Are there some recordings that seem peculiar because the accelerations are too high and the foundation of the recording equipment is destroyed? Thanks.
I can take that on, Eduardo. And to start with the first portion of the question, is this a mega earthquake? By the definition, it is not, because it's magnitude 7.8, but the ground accelerations that were recorded, PGAs and also PGVs, were significantly high. So when we are looking at that, I was part of the EERI team, but I also participated in the gear reconnaissance team. And with the gear reconnaissance team, we actually traveled to some of these very high ground motion recording stations to observe what was happening around the recording station. We were not able to access inside the recording station, but you can observe the structures, buildings around. And for example, for the one that is supposed to record it about 2G of PGA, the response around that recording station was not necessarily showing that it was a 2G. And in fact, in the comments, I believe Ms. Yashem indicated that there was a equipment falling on that recording station. But going on to the codes, I did share some of the recordings and then the response spectra that we obtained from there. The most recent Turkish code is very similar to ASC 716. In that terms, that we can consider it as a modern code, but the recordings in some locations did exceed in the short periods and in long periods what the 2475 year response spectra was. Some of the damage that was observed was related to maybe the lack of inspection during the construction and lack of inspection after these buildings were formed. In several of these cities, the first floors were used as stores or restaurants, where we were told that there were some cases where the columns were cut, and that created the soft story and basically hindered the static of the building. But in addition to that, the one more thing to add is we most of the time design for life safety, because the first earthquake at magnitude 7.8 happened at 4 a.m. and there was a 6.7 like 10 minutes later, and then there was magnitude 7.7 9 hours later. Then this happened in a very short period of time. We don't really know if like most of the buildings, how many of the buildings or the percentage of the buildings basically satisfy the life safety after the first event, but could not satisfy the life safety after the second event. And in that case, then the question comes, is that, do we revisit the modern codes and what we are designing for in terms of life safety versus non-collapse? Eduardo, I know you want to add some additional notes on that one in terms of mega earthquake.
Thank you, Menser. Yeah, so you answered correctly. I mean, in terms of mega, we go larger than 8 usually, but in terms of ground motion intensity, just to put in perspective the records from this event, El Centro North-South 1980, which were in a few days, we were commemorating the anniversary of that one. That one had about 30 centimeters per second. And for many, many years, that was considered the strongest ground motion intensity that we could have. The Japanese paid special attention to PGE for many years, and they consider that 50 centimeters per second was sort of what we should be designing as a very strong ground motion. And if you recall that descending branch, or what Professor Chopra or Newmark and Hall would call that velocity sensitive region of our design spectrum, for many years was this 50 centimeters per second, or 50 kind, as they say in Japan. And then there was an old paper by Jim Broom who wrote that maybe we could see 200 centimeters per second. And a lot of experts thought that was not possible. Well, we recorded several of those. And if we see the number of records that we have collected over the years that have intensities of 150 centimeters per second, this events will basically provide the largest group of that. So it's a very, very important event, and we can sort of see and document the performance of structures close to those levels of intensity for the first time. So it's extremely important event.
Can I just add one comment here that if anyone has any information that would help us answer that question of progressive damage, that will be very important for the community. So if you have access to any satellite data, for example, in between the earthquakes or any information from the locals, please share with us.
I'll pass on to another question. Milad Khatib asked, do you think there's an underestimated approach during the design? Of course, besides that, there's a lack of control during a construction phase. He refers probably quality control, if somebody would like to answer that one.
Yeah, I can get a start on that anyway. Certainly, inspection, construction quality played a role. I mean, to the extent the codes changed after the 1999 earthquake, as Manzar pointed out, not all of that was reflected even in relatively modern structures that we would drive by, at least from what we could see. Inspection is a part of it. Now, we can't say to what degree the engineering was conforming, so won't speculate there. But to the question of are we under designing, these events bring a lot of attention to that question. I think a key risk in that is what you're asking is really a matter of public policy. It's a question for the general public and policymakers, and it's not unique to structural engineering, but in a complex topic, I think things like MCE, things like design basis earthquake, that's the performance that we as a community agree to and understand. But the primary risk being that the general public, even if we performed that anticipated level, says this is way more damage than we were willing to tolerate. So I think it's trying to close that gap a little bit and make sure that the performance anticipated by communities and what they're willing to pay for is what we're providing.
And if we can add to it quickly, it is so true that most of the people did not understand that what the minimum the code was requiring is life safety after the first design event. So, and now in the initial slides that I've shared, 2 million people are left homeless. And that creates significant challenges in terms of providing the basic life needs for these people who are living in still to this day tent cities and container cities. And there is not necessarily a significant set deadline of when they can move into a more stable lifestyle.
Thank you, Mincer. Another question comes from Guillermo Santana, who asked, did you consider communication and telecommunication systems performance during the earthquakes? Ricardo mentioned that they only cover some of that, but Ricardo, can you add a little more?
Communication system in terms of telecom?
Yeah.
We did not cover those.
Observed from the roadway, some relatively large, long period towers, communication towers, microwave and satellite dishes attached. Performance from what we can see from the road was generally good, like other very lightweight lattice structures in the energy distribution system. But we did not get any detailed information on the performance.
Thank you. Unfortunately, we've ran out of time, so I'll just pass it on back to Elizabeth. Just want to thank all of the attendees. We got almost 400, and so thank you for your interest. And Elizabeth, I just leave it to you.
Great. Thank you again so much for everyone for attending today. When this webinar closes, a survey will pop up on your screen, and you'll also receive that by email tomorrow. We'd really appreciate that if you could take a couple minutes just to answer that survey. That helps us make more and better of these events. As I said earlier, you can learn more about EERI at our website. Please join us for the following webinars in this series. Next week, the hospitals team, and the week after, the buildings reconnaissance team. And we're likely to have a fourth webinar, either on geotechnical aspects or on impacts in Syria, potentially on the 30th. And your registration for this webinar will work for those. So if you registered to attend today, you can attend any of those. PDH certificates are available at the link there, which I think will be popped in the chat. And then I just want to say this webinar is supported with funding from FEMA, also by EERI members and by the LFE Endowment Fund. So thank you to all of those for supporting us and making events like this possible.